Hey, good morning, good afternoon, depending what time zone you're in, to everybody. It's good to see some familiar faces up there. How's everybody doing?
Doing well. Thanks for
Glad to,
thanks for hosting this.
yeah, glad to hear it. So we gotta get some messages here. All right. So, for that, with that introduction, so I'm Brian Flegger, the department chair, for those who haven't met me, and I welcome you to the spring town hall meeting for 2025. It's been an adventuresome year, lots of things happening, lots of changes coming through academia, as you're probably aware. I hope to give you some answers and some perspective on where things stand, but the short answer to all of those questions is likely going to be we don't know, and we're waiting to hear. I will do my best to provide a little more specifics as people have questions. But I thought I would kick off the meeting with a really exciting set of activities. So, for those of you who remember last year, in the fall, we had talked about the RISE program. This was a faculty hiring initiative initiated at the provost's office for three specific areas, and that was in artificial intelligence, sustainability, and what they called health span or healthcare, advanced healthcare things. And so through that program, the College of Engineering authorized us to search for five faculty members in these three different areas. And I am thrilled to announce that we interviewed over a dozen different people and made three offers, and all three have accepted those offers. And so I'll begin at the bottom of the screen with Assistant Professor Rahul Sujanani. So Rahul did his PhD at the University of Texas with Benny Freeman, who's a membrane separation expert, and then a postdoc with Rachel Siegelman at UC Santa Barbara, who is one of the best materials synthesis people out there. Really fantastic interaction, and through the Freeman and Siegelman groups, Rahul was the lead scientist as a postdoc to build a DOE facility looking or program specifically looking at membrane materials. And so he's going to bring that combination of expertise, really expand our separations experience. And so he's going to be joining the department here the first week of August. So we're really excited about him. Next up is Joel Paulson. And so Joel recently was going to be promoted at Ohio State. So he was finishing his sixth year as an assistant professor there. And we were able to recruit him away from Ohio State to join us as the Gerald and Luis Batiste Associate Professor. And so Joel is an expert in Bayesian optimization. He is somebody with more energy than I think any person can bottle up. He will be the face, I think, of the department's AI initiatives. He is involved in projects across the spectrum from both fundamental AI techniques and software, symbolic regression, doing things where they're trying to figure out the equations, not just with a correlation, but rather trying to understand the functional forms that would fit those data sets. And so it's a really exciting opportunity for him to come join us, where he'll have a much stronger process systems engineering group with Victor and Stiliani, but then also opportunities to apply his trade across the spectrum of problems, from the life sciences to chemical plant design to process control. And so even he and I are talking about trying to do things in the protein design space. How do we navigate this massive area to try to find the best types of sequences for particular enzymes? And then last but not least, we were able to successfully recruit one of our own, and that's Professor Jeff Greeley, who was one of Manos Mavrakakis's star students a couple decades ago. Jeff climbed the ranks starting at Argonne after he finished his PhD, and then began his professional or academic career at Purdue, where he was a named professor most recently. And so Jeff is a world expert in computational catalysis. So he's one of the true stars in this space. And we are extremely excited to bring him home so that he can augment the things that our catalysis community is doing. His expertise obviously is in density functional theory, having worked with Manos. But his program has diverged from what Manos's group does and is focused a lot on electrochemistry. And so if you remember, we have Marcel Schreier, Matt Gebbe, and several affiliate faculty members around campus who are very interested in this electrochemistry space. And so bringing Jeff Greeley to campus is going to provide that computational collaboration with a lot of our experimental groups. And so we're absolutely thrilled that we went 3 for 3 with these offers. The rest of the candidate pool was fantastic. We actually had no candidate in which we were less than excited when they arrived. And so we had to make some really hard choices in the selections here. But we're ecstatic about these three joining the department. All three will be here in time for the fall semester. So some other faculty news, I would like to acknowledge Eric Schusta's long chairmanship, having set the stage for me to take over the department in a great place. He had a pretty fantastic year as well. He was recognized with the Biotechnology Progress Award for Excellence in Biological Engineering Publication. So this is for one of his research articles. This is an AICHE journal and an AICHE award where he was honored at the AICHE meeting last year in San Diego. And then more recently, he was the recipient of the Kellett Mid-Career Award from campus. And so this is a prestigious award that will provide Eric with additional flexible funding for his research group that he plans to use to help start some new projects as he reemerges from his chairmanship. I'd really like to spend some time talking about Reed Van Lane. Reed is honestly, he's a dynamo. He's one of our, absolute key people in the department. He is involved in just about every aspect, from being a phenomenal teacher, having won a college teaching award in the recent past, to being the chair of graduate admissions for a number of years, and then this year stepping into the director of graduate studies role while Sean Palachek was on sabbatical. And so this year, he received a Vilas Faculty Early Career Investigator Award. This is a really nice recognition from the Vilas Trust for young faculty on campus, as well as then he was named now the Sabota Associate Professor, a title that he'll be able to carry on throughout the rest of his career. I'm thrilled to announce also that Reed's going to be on sabbatical. He's delayed this a few times for various family reasons. But he's going to be trying to develop additional collaborations and research expertise over the next year as he travels around visiting different places. And I believe last fall we had a talk from Quentin Dudley, one of our new professors, assistant professors in the department. And if you remember, he talked about how he was now going to be engineering plants as the medium. So the plant as the chemical factory in thinking of an agricultural way of producing small molecules. And so right now he's in negotiations with the Department of Energy's ARPA-E program in a project that's collaborative with Victor Zavala and Hiroshi Nakaido, a professor over in botany, to do just that. And so this is a really exciting opportunity to try to produce some organic aromatic compounds in particular tissues within the plant cell. And so this is something that we hope is the first of many for Quentin to come. A little bit of student news. So every year we give away awards to the best teaching assistants. These are the Raggett Awards. And so this year, Christian Jurgensen, Josh Eckert, and Haydam Kim were all the recipients. There's a nice picture up here in the top right. And then very nicely, 3 of our undergraduates this year were honored at the Chancellor's Undergraduate Awards Ceremony. So this is a space for the students to be recognized for their both research and academic achievements. Grace Zhang was a sophomore research fellowship. She's been working with Siddharth in the area of hydrogen storage, so a very exciting space. And then Adele Iqbal Abu Hassan, who works with Whitney Liu and is a constant presence around the department because he's either in classes, helping grade things, doing research, and then works a significant number of hours down in the coffee shop. And so we all get to know him quite well. He's actually off to graduate school next year, I believe, at the University of Minnesota. And then Jacob Domro, who's been working with new assistant professor Mai No on developing some of her first experimental techniques. We're all honored with different research awards. A little bit more undergraduate news. So I think with the first issues of Summer Lab taking place in the new Kiddemeyer Instructional Laboratories, we're thrilled to share with you that we had our first real brewing class that happened, or fermentation class, I should say, that happened this spring. And so this was a close collaboration with Lake Louis Brewing here in Verona. And so Kirby Nelson, who is the gentleman here with the beard, was kind enough to meet with me back in January to say, hey, let's revisit an old collaboration between UW-Madison and Wisconsin Brewing, which is now Lake Louie. And Kirby was ecstatic. He jumped at the opportunity. We scheduled something literally within 3 days, and then kicked off this entire course. So the picture down here in the bottom is Kirby with his busted foot, unfortunately, and Brendan Blackwell, one of our teaching faculty, who kicked off the semester course with a discussion of an extra special bitter. This is a London style pale ale that the students were tasked with designing how to brew. And so teams of two designed their own recipe, brewed 5 gallons of this. And then there was a tasting panel right before spring break. And so this is the CEO of Lake Louie Brewing. And there was a panel of additional brewmasters and brewing executives from around Madison. They tasted the different offerings from the students and gave the grades for their midterm exam. And the winning students the winning recipe was selected and brewed here in Oconomowoc. It's a small ballpark brewery that they have at the back end of one of I forget the name of the team in Oconomowoc, but a really nice facility. And so Kirby was able to brew 5 barrels of this batch, and it was available for the students the week of graduation. And so this is a fantastic experience. The students absolutely loved it, and it's something we hope will continue every spring for the foreseeable future. Now, around campus, if I get distracted today, it's because I'm going to be looking at the 1410 building coming down. Actually, I can point to right here. This corner is now destroyed because it was literally knocked down about 2 minutes ago. And so we're working and living in a construction zone. And so the corner of Engineering Drive and Randall Avenue is where one of the major utility tunnels has been worked on. So right now, Randall Avenue is closed for through traffic. We hope to have that back open before football season. But this is the new utility chase that's actually now the recent picture. This is sealed in on top. So it's a full utility tunnel in concrete. And so this is going to extend all the way down Engineering Drive to then access the other lateral that went up along Engineering Center's building to make material science, and will provide the utilities for the new Levy Engineering Center, which we had a wonderful groundbreaking ceremony on April 17th. And so you can see the dignitaries here all came into Engineering Hall lobby because it was a little bit cold that day, and we're able to toss the first shovelfuls of symbolic dirt onto the mat. And so it was a wonderful groundbreaking event that talks about the revitalization of this engineering campus. And I'd be remiss if I didn't mention that earlier last month, on May 19th, we had the dedication of the Weaver Computational Laboratory. So this is the home of the Sierczewski Lab upstairs. And so we had a wonderful program and short ceremony for everybody on that day. And I'll remind you that these donations and these events have helped us to renovate over 40% of our assignable square footage in Engineering Hall. And so these new faculty that we've hired have all been gifted with wonderful state-of-the-art facilities to start their careers. And so we've done, I think, a fantastic job going through this, and we appreciate all the support that alums like you have provided in making that happen. Now, a few of you asked some questions in the registration process, and so this I'm going to provide as information. If we want to go into more details, we can certainly do so in the Q&A later. But college-wide, we admitted just about 6,000 students, and 1,600, and these are all estimates, these are fluctuating quite rapidly, I would say. About 1,600 are planning to enroll. For the department, a little over 600 and 140 were admitted and planning to enroll. Those are numbers that have increased modestly, less than 10%. And then more recently, the progression of freshman students to become official chemical engineers, that process, that number is up about 10% from last year. And so we're seeing a rebound from the dip that chemical engineering across the country had seen. Others of you asked about the cost of education right now. And so these are numbers that are available to you. I'll show you the website here in just a second. So normally students in a semester will enroll between 12 and 18 credits. And so that bottom line there between 7 and 23,000 is what a student's going to pay during the semester. Summer credits vary based on how many courses people are taking, but the summer lab course you'll see ranges from about $3,000 to nearly $10,000 to complete, because that's a 5 credit course. And so if you want to find out these pieces of information at any time, these are available publicly on the financial aid and the bursar websites. The academic 26 numbers will be coming out sometime in July. So we don't have those officially yet. I'm sure that was actually what the question was referring to, but hopefully we'll have more information there in the near future. So that let me then transition now to today's presentation. I think many of you have met George Huber before. He's the Richard L. Antoine Professor of CBE. He did his bachelor's degree at Brigham Young before coming here to work with Jim Domesic as a PhD student. He started his career at UMass Amherst, rose through the ranks there, and then we were fortunate enough to recruit him back to Madison in 2012, where he's been just a stalwart in chemical catalysis, doing everything from fundamental studies up through tech transfer. And so his companies like Anelitech and Galasys, which he may tell you a little bit about today, as well as large research enterprises like the Chemical Upcycling of Waste Plastics, or CUWP, and the more recent Seymour facility, which I think he'll tell you all about. So George, if you don't know, has won numerous awards, notably the Colburn Award from AICHE. He won the Kellett that Eric actually won this year. And he has been one of the most highly cited researchers by Thomson Reuters almost every year since that ranking came out. And so with that, George, I'm going to stop my share and pass the microphone over to you if you want to launch up your presentation.
So, hello, it's good to see everybody virtually. Thanks for allowing me to come and share with you a little bit about my research today. Let's see. Okay, I think you can see my slides. So, audio sounds good. Does it look good? Everything? Okay. So, I'm really going to focus today just on the Plastic Recycling Center that I'm director of. This is the Center for Chemical Upcycling of Waste Plastics. This is a center that's funded through the U.S. Department of Energy. We actually started in 2020. Our funding ends in September of this year. I'll talk to you about some other plans we have to spin off a couple of the technology items that we've been working on with this center. Yeah, I actually wrote the grant for this center during COVID when I was sitting in my son's room trying to make sure he was doing online school. And it turned into the center that involved several faculty in the department and a lot of industry here in Wisconsin. We have a big packaging industry that I'll talk to you about that's really helped me out here to understand more about plastics and plastic packaging. We really live in the plastics age. We use plastics for almost all our materials that all the materials we do, from food packaging, automotive transportation, electrical wires are packaged and we wrap around in plastics material. But there's really a challenge with end of life use. And anywhere from 2 to 5% of your plastics ends up in the ocean, and this is really due to poor end of life use decisions by plastics. There's these open pit dumps, and this is primarily in developing countries. Anywhere from 27 to 30% of the plastics ends up in these dumps. Here in Wisconsin, we landfill our plastics. It's estimated about 40% of our plastics end up in managed landfill, where we basically bury the plastic. We wrap the plastic, and we wrap our trash and other plastics in plastic packaging, and we monitor it to make sure none of it leaks out into the environment. Then 14% of plastics, and these are global numbers, end up in terms of energy recovery, where you burn it. And only about 14% of plastic is recycled. In the US, there's really only two main types of plastics we're good at recycling. That's number one, plastics, your soda bottles. Number two, plastics, your milk jug, primarily your clear plastics. And we're trying to develop more and more technologies to be able to close this loop, get more plastics into this recycling loop. And that's really what we're doing with that cup. And all your plastics comes from oil and natural gas. So in 2020, we formed this center, the Center for Chemical Upcycling of Waste Plastics. We received a $10 million grant from the U.S. Department of Energy. We got $2.5 million in cost share for this grant. The center involves 6 different universities, 3 in the U.S. And DOE wanted to make this a North American center. So we had two universities in Mexico, one in Canada. The recycling problems they face in Mexico are quite a bit different than what we face in the US. And we have one national lab, and we're involved 35 different companies that are involved in this plastic recycling center, including the resin producers, Dow, Sabic, Braschem, SPG. I don't think Lyondell Basel. I think I'm missing SPG on here. No, SCGC. There's SCGC. So we have most of the major resin producers on this. We have a lot of the plastic converters. You can see Amcor, Playcon, Revolution, Val Group. Val Group is the largest plastic converter in South America. And then we have some brand owners in here, Cytiva, Conagra Brands, Estee Lauder as well. And really our goal is to really develop the scientific and engineering principles that will enable the circular upcycling of waste plastics into virgin plastic resins using chemical technology. How can we better reuse our plastic materials? We look at two types of plastics: post-industrial plastic waste that are at industrial sites, post-consumer plastic waste. The first challenge with plastics is all comes with collecting and sorting the plastic. So in Wisconsin and in most places in the US, we have a single recycling bin where we put all our recyclables, and then that goes to what's called the MRF, or Material Recovery Facility. They're really a section of conveyor belts. They have different types of sorting equipment, IR sorters, to sort different plastics. And then they produce baled plastic material. I put high quality single plastic material. It's questionable about how high quality some of these bells are that you get from the MRFs. Most of them are owned by either local municipalities, some are owned by waste management companies, all sorts of quality of MRFs throughout the US. There's no real national standards for the MRFs in terms of the equipment they need, or the specifications on the bells of their plastic. But really, it starts with just sorting, collecting the plastic, and that's a huge challenge that we face in this country. Okay, and then if you do have high quality belled plastics, you can send this to mechanical recycling. Like if you have a bell of soda bottles, you can mechanically recycle it, make rPET, RHDPE. This is recycled PET, recycled HDPE. And you'll see a lot of companies that use this recycled PET to make different materials, remake the soda bottles. Coca-Cola, they have 100% bottles that are made from 100% rPET that you can actually see when you go to the a grocery store vending machine. Then another type of technology that's being developed and commercialized is thermal depolymerization, where you take your plastics, you heat it to about 500 to 550 degrees C, you make this oil. Okay, and there's about a dozen companies who have made announcements where they're building commercial pyrolysis plants. Huge amount of industrial interest here. We're trying to understand the fundamentals of the chemistry that's occurring here and characterize this oil. Okay, you then often hydrocrack it, and then a lot of companies are using it as a feed to replace naphtha in their steam crackers. And so then you make your olefins. You can separate these out by a certain portion out by mass balance, and then you can sell 100% recycled polyolefins or different recycled material. And then the last technology I'm going to talk to you about is our solvent-based technology called STRAP, where we use solvents to be able to purify different waste plastics. We make pure resins, and we're looking at spinning this off into a startup company. And I'll talk to you about that later on at the end of this presentation. So the first technology I'm going to talk to you about is pyrolysis, and then I'll talk to you about the strap-based technology. This is our feedstock for pyrolysis. This is really ground. You can think about this ground detergent bottles. We'll take your Tide bottle, you grind it up, and you have here your feedstock here, mixed colored HDPE. Here's our fluidized bed reactor that we run in University of Wisconsin that my graduate student, Jiayang Wu, who just graduated last week with her PhD, worked on for 5 years. And you make this oil, okay? Usually we distill it into a light oil, a heavier oil. and we separate it by a boiling point of about 165 degrees C. Our yields, about 50 weight% of the plastic ends up in this light oil, 18 weight% ends up in this heavy oil. So then the question is, what is in this oil? What do you do with it? Okay, so we've spent a lot of time analyzing what's in this oil. You have a huge distribution of products. There's light gases from C1 all the way up to heavy waxes C40. And you can see it really contains large amounts of olefins. You pyrolyze a olefin, you make a monoolefin. It shouldn't be too big of a surprise. You also see some alkynes, but there's a range of products that you make in that oil. And this really ties to oil refining. When oil refining was first developed, the first thing that you did was you distilled it and you sold the kerosene, okay? And then you threw away or burned everything else. Over time, they started pyrolyzing the heavy oil, just heating it up thermally into gasoline, kerosene, a light industrial fuel. Over time, they developed the Howdrey process where they say, okay, let's introduce catalyst into the pyrolysis reactor to convert it into oil. Some of that oil in the gasoline, they got higher yields. And then in 1942, they took that heavy cut and they added alumina silicates to in a fluid catalytic cracking to convert that more of that heavy oil into gasoline. And then over time, they developed better and better catalysts that went into this FCC process. My opinion is most of industry, when we look at the waste polyolefins, we're really here today. Really, we're just almost all these technologies are pyrolysis. There's our companies that are developing new ways to add catalysts into this pyrolysis reactor to get higher yields, make other products from this. So when we analyze the oil, and one of the things we did with CUWP, the first thing we did is let's analyze the oil, make sure we understand the chemistry that's in the oil. So what we can see is this pyrolysis oil. Here's 3 different pyrolysis oils, one from HDPE, this one from LDPE. Let me turn on my pointer here. And this one from polypropylene. They all have a lot of green here. Green are the monoolefins, and blue here are the diolefins. So there's really high concentrations of olefins in these pyrolysis oil. In the crude oil, there are really no natural sources of olefins. It's only really through the refining process you introduce that olefin functionality. If you look at naphtha, it's mainly paraffins, naphthenes, and aromatics. Diesel fuel, there's very little. Gasoline has some olefins, and that gets put in during the refining process. So, we said, let's not use this oil to feed into a steam cracker, but let's use this functionality of the olefin for the chemical, that chemical functionality. So we applied a chemistry called hydroformylation. This is the hydroformylation chemistry. We'll go back to organic chemistry. You take an olefin, we add CO and hydrogen to it, and we make an aldehyde. We can either make a linear aldehyde or a branched aldehyde. And we took that oil I showed you, we apply it, and you get almost 100% yield of the olefin into this aldehyde. So, and we can take this, and then we can hydrogenate this into alcohols to make surfactants. We're actually working with a few companies to try and take the waste plastics, turn them into surfactants, make other polyesters, plasticizers with this. We can oxidize those aldehydes, or we can aminate them as well to make amines. So really, it's a new type of chemical feedstock, this pyrolysis oil, that we can exploit the chemistry of to really make new functionalities that are used to make a wide variety of chemicals. This is technology that's in the lab that kind of spun out from CUWP that we're continuing to work on and try to develop. Ho-Chin Lee worked on this. He's now a professor at New Mexico State. Jiayang Wu worked on this as well, and she just graduated with her PhD last week. So that's the pyrolysis technology. Now, the other technology I'm going to talk to you about is STRAP. Shortly, we're going to spin this off into a startup company, and they put together this nice investor presentation that I think kind of provides a good explanation more about STRAP. There's really a huge unmet demand for recycled plastics. We estimate in North America, Europe, and Japan, there could be over a $25 billion market per year for these waste plastics. Most of these waste plastics are not recycled today because that technology doesn't exist. Packaging is a huge amount of the plastic industry. It's about 40% of the planet's plastic waste is packaging material. Okay, and mechanical recycling works very well for clear, rigid materials, the soda bottles and the milk jugs. You know, we're very good at mechanical recycling. I don't think we'll compete with strap in that, but there's all these other plastic materials, super polypropylene super sacks, your flexible films, your plastic wrap, shrink wrap, plastic bags, this polypropylene biaxial oriented laminated polypropylene bag that really the technology isn't there for recycling it. And there's a huge number of companies. Almost every single consumer brand company has made goals to increase the use of recycled plastics to do different targets. Here's one sustainability goal you can see with Amcor. They want 100% of their packaging to be reusable, recyclable, or compostable. They're taking ambitious goals to effectively recycle, compost 50% of their packaging by 2025 and have an average of 30% recycled content by 2025. So all these companies have made these very ambitious targets to use more recycled content in this. In the EU, you're seeing a lot of legislation that's mandating this. And one thing I've learned with CUP is how many people are involved with the plastics. Okay, so I put together this diagram here. You have the refineries who extract the oil. You have the companies who make the resins. You have the converters like Amcor who make the packaging material they purchase from companies like Dow Chemical. These are companies like Amcor that make the packaging material. You then have the brand owners like Coca-Cola who buy the packaging material, put their product in it, sell it to the retailers. You have the consumers who use your material. Then you have the waste management company who comes collect your trash. And then you have the people who own the landfills. Oftentimes it's the waste management company. Sometimes it's the municipality. So all these are the stakeholders that are involved with plastic recycling. You know, right now you do have the MRFs. Okay, so a few mechanical recycles in Wisconsin. We only have one company who can make recycled PET, food grade recycled PET. And what we're trying to do is, you know, STRAP will enable more of these people to get more of these streams back to the plastic converter. Pyrolysis really makes sense if you're near a large polymer petrochemical complex like in the Gulf of Mexico, but in Wisconsin we're far away from that. So that's why we need a technology like STRAP where we can make the pure resins. We can produce high quality resins that are very similar in property to the virgin resins. We've been able to process over a dozen different feedstocks to remove different components from that plastics. You're using standard equipment that we believe is very scalable, and our emissions has more than 80%, up to 80% reduction in greenhouse gas emissions compared to the virgin plastics. These are some of the feedstocks that we've worked on. This is a printed film. This is a reverse laminated multi-layer polyester film manufactured by Amcor. We've worked a lot on this material. We can pull off very high quality polyethylene from it. This is a mixed film waste, a waste stream that you get from the mixed film. When this is used shrink wrap, and we just took the shrink wrap, we kind of compressed it into this film. And here's our material, what it looks like after STRAP. It's very clear. We've had this tested in Amcor. We made compressed films. They say the quality of it is a lot better than the PCR polyethylene that's on the market today. This is the PCR polyethylene pellet that is on the market today. You can see it's gray, it smells. This is a lot higher quality material, but if you look at you buy a 6-pack of soda, you'll see it looks gray. It's made from material like this. There's not a lot of uses for this. It's a lot higher quality material. This is a virgin LDPE material. We can get our materials to really look like those virgin materials and really remove the contaminants. This is kind of a simplified diagram of our STRAP process. It starts with shredding. We dissolve it. We do a lot of filtration there. We then precipitate it, remove all the solvent, recover the solvent, purify it, resend it back, and then we make the pellets that would then go to the plastic converter. So, the advantage of us is we're making high quality plastics. We're dealing with complex feedstocks. We can process a range of plastics, and it's fairly low energy and pressure compared to other technologies like pyrolysis, or the largest solvent-based technology company that's on the market today is a company called Pure Cycle that's in Ohio. And we've been fortunate to receive a large amount of federal funding on this. We have about 9 graduate students in our department that are working on this, that are being supported. We've been protecting this. We have 4 pending patent applications that have been filed in the last few years. 15 plus peer-reviewed publications continuing to do this. Lots of industrial collaboration. We have a couple of companies who are sponsoring this. We've worked very closely with Amcor. They've validated our material. They've written papers on us. Their engineers have indicated a lot of interest in this. And then we need to scale this up. So it's nice we can do this in the lab, we can make kilogram quantities in the lab. So we've designed this pilot plant at Michigan Tech. We spent probably over $5 million purchasing the different equipment. We're assembling this pilot plant. We hope it'll be operational by the end of 2025. It's designed to operate about 25 kilograms an hour and really validate each component of this strap process. So our goal really is we want to have the pilot plant constructed by 2025. Late 2025, have some initial operations with this, do more detailed design operations in 2026. And then we hope to have a business that's cash flow positive by 2029. And then our unit economics are very promising. We see more than a 55% gross margin. That as long as we're large enough in scale, we can really compete with virgin plastics. And we're in the process of forming a startup company, raising money to kind of validate our pilot plant and really bring it to the market. So there's a lot of people who are involved with this company. Brian Flager talked to you about Reed Van Lane. He's been very instrumental on this. He does a lot of our computational modeling with this. We didn't have a place to build the pilot plant at UW, so we went to Michigan Tech, and we're working with a professor there named Ezra Barzeev. Charles Granger, who's a PhD student of mine, very interested in entrepreneurship. Our goal is for him to become the CTO of the startup company. Bob Rosemerk, another has a bachelor's, master's degree in chemical engineering. He worked for another spin-out company here in Madison called Byron Energy Systems. He's really our entrepreneurial lead with a new company who's looking at commercializing this. So thank you for allowing me to talk about this strap technology and pyrolysis. I'll be glad to answer any questions.